This will be a very short video because it's sort of a recap of the previous one. So we saw that to change the basis of a matrix, we can use the relation a to the minus 1 times m times a, where a and a to the minus 1 are the change of basis matrix and its inverse, and where m is the original transformation in the old basis, and m prime is the same transformation but written in the new basis. So that is called a similarity transformation. So let's write it here. M prime equals a to the minus 1 times m times a. Now, what if you had m prime and you wanted to calculate m? So how would you do it? Well, that's fairly easy. So imagine you have m prime, which is this. So first we multiply by the inverse of a on the right. Okay, so to every matrix we add the inverse of a on the right. Oops, sorry that you didn't see this. So we have started with this equation and we multiply times the inverse of a on the right. So we arrive at m prime inverse of a is equal to inverse of a times m times a times inverse of a. But a and inverse of a, they cancel out. Okay? And now we multiply on the left times matrix A. So we get a times m prime times inverse of a is equal to a times inverse of a times m. But a and inverse of a cancel out, and we arrive at m equals a times m prime times a to the minus 1. So we have reversed this condition. So let's write it here. M is equal to a times m prime times a to the minus 1. Okay? If we looked at the previous diagram, this is like saying that m can either go directly or we can go using this path. So this path is first a to the minus 1, then m prime, and then a, which is what we are doing. First a to the minus 1, then m prime, and then a. We go from right to left applying transformations. Excellent. So these are called the similarity transformations. And when this happens, matrices m and m prime are said to be similar matrices. It's a funny name, but they are technically called similar matrices. Okay? So whenever two matrices are related in this way, they are called similar matrices. And similar matrices, let's write some important things about similar matrices. They represent the same transformation. Right? Do you remember the example I gave you where we had the projection into the x-axis and we could either write it as matrix M in the basis x hat y hat or as matrix M prime in this new basis B1 and B2. Let me fill in this matrix very quickly. If you actually did the calculation of a to the minus 1 times m times a using a as the change of basis matrix corresponding to this basis, okay, so a would be equal to, in this case, the matrix 1 1 1 minus 1. So doing those operations, you would arrive at matrix m prime being equal to this matrix 1 half 1 half 1 half 1 half. And indeed, if you multiply this matrix times this vector, you end up with this vector. Okay, so this matrix, it might look different because it has different numbers to matrix M, but it's actually representing the same projection into the x-axis because it's converting the same vector into the same output vector, just that the vectors are written in a different basis. That's why the numbers, the specific numbers, are different. Okay, so these two matrices, they represent the same transformation. Since they represent the same transformation, there are other interesting conditions, and it's that they have the same determinant because they represent the same transformation. So they have the same determinant. Okay, so indeed, in this example, the determinant of this matrix is 0, and the determinant of this matrix is also 0. Not only that, but they also have the same trace. So if you add the elements of the diagonal, here you get a half plus a half is 1, 1 plus 0 is 1. Same trace. Okay? Not only that, but they have the same rank and the same nullity. Of course, they represent the same transformation. Of course, they have the same rank and the same nullity. They also have the same eigenvalues. And finally, they have the same eigenvectors, but written in the corresponding basis. So when you calculate the eigenvectors, you won't get the same numbers, but you will get the numbers that correspond to the same vectors in the corresponding basis for each matrix. So same eigenvectors, but written in the corresponding basis. Okay, so this was it. These are similarity transformations and two matrices that are similar matrices when they represent the same transformation in different bases. Thanks for watching. In the next video, we will do an example of calculating m prime knowing m.